Ladies and gentlemen, please take your seats. The workshop is about to begin. Thank you.
I don't wanna take one breath without you. Oh, and I don't even know one thing about you.
Hello, everybody. Thank you for coming back. And if you're just coming in, come down and sit towards the front. There's plenty of room. So in this session, I'm going to explore in more depth some of the ideas we talked about earlier. I hope you've all had a good lunch, a lot of coffee, feeling pretty energetic. I'm going to talk for about 30 minutes. I'm going to talk about some of the non-technical aspects of data science, and then end the talk with the fun and technical parts. And if you have any questions, we're going to have 10 or 15 minutes for questions at the end, and there will be folks with microphones. You should start thinking about them now. And just how many people here are data scientists? I want to get a sense. We've got a couple brave folks. All right, thank you. And how many people here are working on the business side of data science? So we've got more of you. All right, you outnumber us. And other folks, is there anyone here thinking about data product development? No? All right, so I don't know what the rest of you do, but hopefully you'll enjoy the discussion, and we'll take it from there. What I'm talking about today is really how we think about building data products, and there are multiple perspectives we're going to take on that. So one of those is, of course, the technical platform. What are the machine learning capabilities, and how do they work? The second one is who does this work, and how do they work together? And the third is what the heck do we do? What does the opportunity look like? How do we get there? And so we're going to go through those layers of meaning today, and hopefully have some fun doing it. And I wanted to kick off this presentation with one of my favorite examples of big data. And so if you look at this slide behind me, you'll see on the left side here is a machine. And this is Herman Hollerith's census tabulating machine. And it was actually a couple years ago, I was writing a talk for an open source Python development conference, and I was thinking, really, where does this even come from? What's the first example I can find of big data? If we think about that being data, or things we wanted to count in the world that we could not count just with our human devices alone, we needed to create technology to do it. And I found this patent written by Herman Hollerith. You can actually Google the patent, and it's very readable. It's really beautiful. And he designed a machine for counting the US Census, a single-purpose machine. And it was because he realized in the 1880s that the population had grown to the point where counting the census was going to take longer than the 10-year interval in which we had to do the next census. He realized we needed technology to solve this problem. And he had this idea, which he was inspired by rail ticket takers, conductors, and the way they punch cards. He had this idea that we could use that same mechanism to count people, and he built this machine. And there's another reason I include the photo here, which is that it used punch cards, right? And the punch cards were initially the size of US currency at the time. It was slightly bigger than current US currency, because he got a bunch of US currency boxes cheap. And as engineers, we know there is always a reason why things are the way they are, and you can actually look at those original punch cards to the refined punch cards that were used on systems like the IBM 1401, all the way down the line to languages, programming languages that were created that were based on punch card data formats, to some of the work we do today. There's a long chain. Now, the second reason I'm starting with this historical example is because Herman Hollerith created a company called the Tabulating Machine Company, which is a really terrible name. And so when it merged with some other businesses, it eventually was called International Business Machines, or IBM. And again, IBM brings us all here today for this conversation about data. So we'll start off in the 1800s, and now we'll go to 2017, where we have headlines like this: teenager teaches AI to rap like Kanye, right? This is the world we are actually living in today. And it's one with more and more data. And so any talk like this, of course, has a slide with lots showing how much data there is in the world. And there's more and more all the time. I love this graph in particular because it goes both up and down and to the right. But this is really about making the world countable. So in the same way that that census counting machine let us count people, it made the world computable, we today, carrying our cell phones and our sensors, are making our world countable in a way that we haven't before. And that's really exciting. And we can't talk about this stuff without having a level set on terms. We did a little bit of this earlier, but I want to go into more depth. When we think about this, if we were having this conversation 8 years ago, we would be talking all about big data, data lakes. What that is getting your data in one place so you can query it. That's all. So before that, and I expect some folks in the audience here today are probably, may not even remember, you would have data in multiple different systems that could not talk to each other. There were many companies that could not do one query across their customers in every product they offered. And some of those are still the case today, it's okay. But that's what big data is. It's about getting all your data in a place where you can actually query it. And the second thing is what you do when you can ask questions of your data, when you can count things, which is analytics. You have questions, you find the answers in your data. That's analytics. It's very straightforward. You're counting things. Data science is where we start to use algorithms. We start to count things cleverly. We want to predict things. We want to use data to add nuance to our understanding of the world. Maybe you want to build some models. That is counting things cleverly, and it relies on that ability to do analytics, and it relies on that data infrastructure. And then machine learning is counting things cleverly with data feedback loops. So you design products that have algorithms in them that get better with the introduction of more data. And if you design them well, you build these virtuous cycles of improvement where with every new generation of the product, you've now opened up new opportunities by using the data that you have. And then today we also, now in 2017 in particular, started talking about AI again, which I'll just say is sort of an umbrella over all of these capabilities. It's become a little bit of a general term for anything cool you can do with data. So that's what I'm going to call it. And again, when you think about data inside complex organizations, it does a few different things. So the same technology and same math can be used for analytics. It can be used for product data science and product features. And as you know, business problem reporting and building recommendation engines, spam filters, search algorithms, very different mindset, same technology. And it can be used for R&D, where you're opening up new product opportunities, new business opportunities by using the data you have, either to identify insights that no one else has about the world, or to actually build a new product with some sort of automation capability. So that's what we're doing with all this stuff, and we'll call it AI. And data-driven businesses are a little bit different than traditional businesses, and what makes the products great is different. So I'm going to show you my favorite data product of all time. This is Google Maps with the traffic view turned on, and I always ask this question. It's a little bit of a trick question. What is the most interesting thing about this product? Why is it great? All right, I said it was a trick question, so no one's talking. Hopefully that's the reason everyone's so quiet. It's tremendously boring, right? So we can look at this product. This is, I think we're in Philly here, but it doesn't matter. So anyone who grows up in our society learns to read maps like this. We learn that red means bad and green means go. And you can be driving your car down the street, looking at a device and actually making a decision based on the data you see in that map in real time, such that you have a better experience of driving without any awareness of the technical achievement it took to build this product. And so when you actually think about how this works, they're taking historical data and making predictions. They're getting real-time data from all the devices that are out there traveling on the streets. They're integrating all of this and other data sources besides, and they're streaming that down to your mobile device in near real time and then visualizing it for you in a way that you can make a decision with a 10% of your attention. And that is amazing. So the best data products are the one in which the data capability fades into the background. You don't even have to know that it's a data product. Don't even have to think about the technology. in order to benefit from the utility. And so when we try and create data products, at least in my company, that's what we're aiming for. We're aiming for things that are so useful, people do not care that it's machine learning on the back end. And this is really hard to do well. And part of the reason it's hard is that it's a fairly new opportunity. And it's not new. The ideas have been around for a long time, but the technology that allows us to play with data in this way to build these systems is new-ish and changing rapidly. And I just said Google made my favorite data product of all time. So I am going to share with you a personal example of where things could go wrong and what it feels like to be an edge case. In this particular example, so my name is Hillary Mason. Hillary has one L in it, and I share this name with a British character actress named Hillary Mason. And she unfortunately was quite a bit old, well, she's quite a bit older than me. She passed away after a very long and successful career in 2006. And so, I was sitting around in 2009, and I tried out this new search engine called Cool, and it was supposed to be a Google killer. And you can see, like, in my browser tabs in this picture, Google Reader was still alive. Like, this was another era on the internet. But they had an entity recognition resolution problem, because that was my bio at the time. And that is Hillary Mason, the actress, playing the role of ugly hag in a movie, right? So this is not cool. And this just speaks to the problem with being, an edge case and having that overlapping name. But you might think, okay, that was a startup. They didn't know what they were doing. They were young. So a couple years later, Microsoft, which has the Bing search engine, which is a great search engine, rolls out their, sort of famous people blurbs. And as you see here, that is my picture, better haircut, but my picture. That is not my bio next to my picture there. I did not die in 2006. I am, in fact, not a zombie or a vampire. I am here talking to you, nor am I an actress. I'm a computer scientist. And so this is really hard. It's something they've solved for very common names. I'm sure if there's a John Smith, they've rigorously reviewed everything. But for weirdos like me, you keep messing it up. And you might say, oh, well, that's Microsoft. Who knows what they're doing, even though their technology is fantastic. Well, here we go to Google. And this was, again, a couple years ago. And if you searched for Robot Jox, which, by the way, was one of the other Hillary Mason's finest theatrical moments, it was in the 80s. It was a film about giant robots fighting. That is my photo there on Google, sneaking in there. Of course, I know a lot of people who work at Google, so as soon as I start making fun of them, they take it down. And then a few months ago, I was giving a data engineering talk, and I went to see, I was like, oh, I wonder if there's any chance it's still going on. And there I am again, just a few months ago, having snuck back in there. I'm not even sure what event that photo came from, but somehow, even one of the companies that is fantastic at this still can't get it right every time. And that's because this is really hard. And unlike software engineering, where I'm pretty sure that if I go to any of your companies, you do software engineering pretty much the same way. So there are only a couple of processes you follow around software engineering, agile, waterfall, whatever that may be. But when I move from one company to another, they're essentially the same idea. Details are a little different. Data product development is different everywhere. Everyone who does it well does it differently. We have yet to develop that consistent professional practice, which we will over the next few years, but it's still to come. And a lot of the time we think, especially because we do a lot of work in the startup community as well as with large companies, that the startups have a huge advantage. And I'll tell you they don't really, because they have no data and they are resource constrained. And so most startups are not inventing technology. They have no proprietary data that's interesting. They are using commodity technology to solve new product problems, new business problems, but that's not where the real opportunity is. The real opportunity is in folks who have been operating a business for some time, who have generated a large amount of data, generally as an exhaust process of running that business, and are able now to take advantage of it. And that's where a lot of opportunity lies. Now, of course, the challenge in those environments is much more people and organizational than it is technological, but there you go. And we're starting today to see the actual value coming out of machine learning. So if we were having this conversation 3 years ago, people would be very skeptical. They'd say, okay, who's actually doing this well? Who's actually doing this at all? Why should we even think about it? But we're getting to the point where enough people are creating value out of it that you can no longer ignore it. Or at least that's my argument. You may disagree. And part of this is that data science is a new professional role. And so I'll ask the data scientists in the room, how many of you had the same job title you have today 5 years ago? Okay, no one's raising their hands, so I'm going to say that that supports my argument here. What we do as data scientists is not new, and this is generally how I like to think about it. It is 3 professional disciplines. So we have the quantitative statistics, the ability to do mathematics. And again, we've been doing this for a very long time. Obviously, we've had mathematicians for a long time. It is the ability to write code, to interact with software systems, to be able to make a model and apply it to the data wherever the data lives. And again, a few years ago, I actually had an on-stage live debate at the Strata Data Science Conference about whether you had to program to be a data scientist. And I argued yes, and my side won. But you don't have to be a professional engineer. Software engineering is its own profession. But you do have to be fluent enough with the technology in order to take the model and get it implemented, scaled, deployed, and all that. And the last thing, I called it communication in this picture, but it's really about asking the right questions. It is figuring out what to prioritize. It is being able to see someone who has a problem, go away and put together an analysis with the data you have available and the tools you have access to, and then go back to them and explain what you learned so they make a better decision. And so what makes a great data scientist is not just the mathematical skill and the technical skill, but it's this ability to prioritize, to work on the right problem that will be impactful, and to know when you have a chance of so many data science opportunities are taking a system that already exists and making it 1% more efficient. Sometimes that can be hugely valuable, but often you also have chances to take a system and make it an order of magnitude more efficient. And those are the ones you generally want to pursue, at least at first. And that means we need leadership who understands data science. Even if they're not data scientists themselves, they need to be able to take organizational priorities, translate that to technical problem statements, and then get out of the way. And by that, I mean you have to understand that data science, when you start a problem, you don't always know if it's possible to solve it. But you need, in order to succeed in this, you need both strong leadership and strong people doing your math and writing your code and thinking about the problems to work on. And that means it's a team sport, and that's been a theme we've explored throughout the day. But what I mean about this is that data science, you can now get a degree in it, but you couldn't until 3 or 4 years ago. And that means that most of us come from very different backgrounds. You know, plenty of data scientists with PhDs in science, plenty of data scientists who are social scientists, plenty of data scientists who are engineers who like math a lot, and even data scientists who are really great at visualization, data storytelling, and taught themselves the other tools. And so people come to this with so many different points of view, and sometimes this leads to a little bit of lively bickering, but often it just leads to a better outcome from having a team. And another question we talk about often is, where in the org does your team sit? And to me, it doesn't matter. There's within each company, there's a right answer and a wrong answer, but generally you want to give your data scientists a mechanism to collaborate together, because they will learn from each other and make each other better. And with every piece of work they do, they will set the bar higher. Now, another issue we hear is one around human nature, intuition versus data, as if this is some kind of battle where we're going to have one or the other, where you either have a job or you've been replaced by one of those talking robots. And that is actually the wrong debate to have. It is much more around, how do we use data as a tool to inform our intuition, to take the assumptions we make that we base our decisions on and validate them and extend them. So how do we do that well? And when we actually see people go ahead and invest, someone this morning said, you know, there's 2 kinds of machine learning projects. There's cost savings and there's new revenue, which is a great language to use around this. We always see people invest in identifying high-value problems where automation will make it cheaper to do the thing you already do. So find processes where people are using information inefficiently and make it more efficient. Help people make decisions more efficiently. And we're seeing a lot of success with applications like people in customer service, where you have a chatbot not to have some sort of brilliant conversation with the user or the person who has a problem, but to identify the kind of problem they have and what the action might be, and then to get that in front of the human customer service representative to make a better decision about what to do. But once you've built that first round, then you can start to think about those new revenue opportunities, because if you do that first round well, you have built some infrastructure, some intelligence around your data that you can build on to enable new products. And that's where the larger opportunity lies, but it's very hard for someone to invest in a project that has an unknown ROI. Much easier to invest in one with a known ROI, even if it's small, versus an unknown, new innovative idea. And so my advice to folks, especially people who are always like, I want to start doing this now, is start with the first one, but do it with an eye towards the second one. And that's how you actually get going. And outsourcing here is difficult, so this is something that should be owned inside the company intellectually, the whole process. You can't outsource your own business, which is what your data is. And along those lines, if you just want to buy a solution, there's your problem with your data, and then there's the generic version of that problem, which would solve everybody's problem in that class of problems. And the majority of machine learning applications are not easy to solve in that generic formulation, which means that you have advantages, you have abilities to do things inside your company that you can't buy. And so we often see a lot of opportunities going unpursued because people think, oh, data is a technology problem, I'm just going to buy the solution from a vendor. I don't want to build and own anything in-house. But there are things you can do that you cannot buy because of this. And it's a really interesting little quirk of our market today and our technology that this is where we are. And so a good rule of thumb for machine learning, first, can a human do it? Second, can a group of humans do it consistently? And if the answer to both of these questions is yes, you can probably make some progress with machine learning on that application. Again, just very simple way to think about the framework. And the culture of data science is really important. Culture being how it's the default actions people take when they're not told what to do. But in data science, it means a shift from a purely deterministic culture, one of engineering. That is, we're going to build that, here's the spec, and we're going to do our iterations till we get there, to one of we're going to talk about some ideas, we're going to do science, we're going to investigate which ones are possible, we're going to pick a portfolio of different initiatives, and out of that we expect some percentage to actually yield value, but we don't know up front which ones. It's a really different way of thinking about product development. It's a little more fun, in my opinion, too, but it does require having a process. And so for data scientists, the first thing you need to do is say, what is the problem we are really trying to solve, and write it down in plain language that anyone can understand. This is the data science problem statement. Doing this is harder than you think it will be. The second thing is, what are our error metrics? So how do we know when we've won? How do we know when we have a successful solution to this problem? And the reason to ask this is so that you actually do know if you have met your goal, the goal you had when you started. Also because data scientists sometimes get caught up in how exciting a piece of work is, and they may go down some rabbit hole, and if you don't have a means to say, okay, you're done enough, this is sufficient, you won't pull them back. You might see them 2 months later and they've gone from something really order of magnitudes impactful to like working on that last 0.01%, and it's not a great use of their time. So really, error metrics, very important, especially quantitative ones. And if we do succeed in answering this question, building this solution, creating this model, what is the first thing we'll do with it? And this is worded very carefully because you should always have things in mind for the second and the third thing that you'll do with it. Don't do work in isolation. It should always give you something to build on top of. And if you sort of follow this general process, it's a scientific process. It's one of exploration. It's not engineering. And that's the difference between what we do now and data science. All right, so I know you're awake because I have a cat on the screen. I want to end this talk by talking about technology, which is my favorite part, and hopefully will leave you with the best part of the whole discussion. At Fast Forward Labs, we do a bunch of things. So we are an applied machine learning research group. Every quarter, we do a report and a prototype, and I want to show you some of them. We aim to be about 6 months to 2 years ahead of what is common in the market, and explain sort of why we think it's interesting and impactful and what it means for data science opportunity going forward. And then we'll have time for questions, so thank you for bearing with me. We work with 3 different communities generally, and we are a bridge between them. And I also believe something about data scientists and engineers as well that is not always a common belief, which is that technical people can actually speak clearly, can communicate, and can talk about what's important about the work that they're doing. And our work involves spending a lot of time in the research community, a lot of time with startups, sort of looking at different applications, seeing where they're going to go, and then also folks in enterprise. And sometimes that means that, in research, we might say, oh, you have a RAID array, and in startups, we say, oh, you've got, Hadoop deployed somewhere, and in the enterprise, we say, oh, that's your data lake, right? The same essential idea, but making sure that the idea is translated from one community to another. And this is true with technical capabilities as well. And so we have 2 things we try and do. One is interesting research, and the other is helping people build excellent data products, not mediocre data products. We have a pretty strong point of view on that. And every quarter, we write a report, and that is a lovely book. We have them letterpressed in Brooklyn. It's very hip. That sort of goes through what this thing is, why it's interesting, how it works at a conceptual level, so for the CEO, how it works at a technical level for the people who are actually going to be doing the work, any ethics or regulatory issues, a prediction for where it's going to go in the future, 1 to 5 years and beyond, and sort of anything to think about when you actually want to go and build a product with this. And we build working prototypes for each of these. And this is a great way for us to go very technically deep on one topic, but then also to put it out there in the world and see what people are doing. And so these are a few of the ones I'm most excited about, one of them being natural language generation. That is taking small amounts of structured data and generating articles and narrative. And if you hear about this at all, it's because reporters are totally freaked out about this because they think it's going to replace their jobs. But it is not, because you cannot use it to generate writing that is not similar to writing that has already been written. And so to explore this, we wrote a prototype that lets you put in structured data about a New York City apartment, and it writes the advertisement for you. And what's interesting about this technology is not about replacing journalists at all. It's that you can take complex data. Very few people love to stare at columns of numbers. I learned that the hard way. So typically, we might show them a graph and say, OK, you still have to do the work to interpret what that graph says. But now we can just give you a sentence that says, here is the thing that you can abstract away from that data. And this is being used now. We've got one client using it to automate reporting around celebrity gossip. So, Justin Bieber does a thing, and there's an article that it's highly structured data, believe it or not, to generate compliance documentation for a bank, to report on people's retirement portfolio performance. So lots of applications, the same technology, but making data clear to people through language. And another one we're very excited about, of course, is the use of deep learning to look at rich media data. I used to be the chief scientist at a social media analytics company called Bitly. At the time I was there, something around 16% of links were primarily a media object, that is video, photo, audio, and we had to throw it away because until a couple years ago, you literally could not analyze that data in any reasonable automated way. And the companies that were doing it were generally sending it to Mechanical Turk or to humans somewhere to label that data. But now we have neural networks, which allow us to actually build something like this. And one thing about giving a talk like this is I can't talk about anyone else's mistakes, but I can talk about ours. And we built a tool that lets you put in your photos from Instagram, and then it says, oh, here's a visualization of what you like to take pictures of. And the first time I put my photos in, it told me I like to take pictures of prisons and correctional institutions. And I thought, well, that's not right. It turns out I take pictures in the New York City subway system. I live in New York and I get bored waiting for the train, and so I take a lot of pictures. And there was no subway or public transit data in our training set, and so prisons were the closest thing, which tells you something about New York's infrastructure. But I wanted to share this other one with you, which is a restaurant. I love burgers, so Bleecker Burger, I put it in, and all of their photos are cheeseburgers except the one on the lower right, which is a flagpole, so it got that. But it says, okay, hamburgers, that's right. Dishes means things that knows are food, but not what they are. But then crabs, so why crabs? And if you look at these photos, you see that anything that's French fries or potatoes next to a dock or water is being called a crab, because the system has learned the label crab has things like this that are near water or a dock. And this is wrong. And so I share this also because even though this technology has incredible power, we have to be really aware of where it can go awry. And it can be used for amazing things. So we've seen some projects where people are using real-time video off of surgical devices to detect when a surgery goes awry. We have a media company using this to catalog 20 years of their back catalog of video that the producers at the time had been too lazy to tag properly or didn't spell things right. Just huge advances in what we can do with this data. But there's still a little bit of caution to be taken. You can also apply neural networks to text, and so this is something really cool. Summarization is a nice form for it. So you can take an article. This is one of our prototypes. You can parse the text out of the article, and you can, on the left side, you see a column of sentences that contains the same information contained in the whole article. And this is cool, but it is something that just sort of makes it easier to do something you were doing before. Like you could read the article, you can read the short version. But you can imagine now we applied this to a corpus of 10,000 articles. We took Amazon product reviews, and we're able to say, oh, here are the 10 points of view in this corpus, and here's a summary of each one. So you take it and you apply it. You start with something you can do anyway, and then find an ability to scale that to something that you just could not, as a human being, do before. And that's the kind of application I get pretty excited about. And what this is doing is making language computable. It lets you represent sentences as vectors of computable numbers, essentially, that can be compared and modified in interesting ways. And we're seeing people do a ton of interesting stuff with this. Everything from an insurance company that has handwritten applications that's now able to cluster and understand who's applying for their product in a way that they had this data forever, but they were never able to actually learn anything from it because they couldn't process it. All the way to investment managers who are now able to take their 5 dominant data sources, which are really these news feeds they get in their email, and automatically get it in a format that's much quicker for them to read to get to the decision they need to make. And the last one I'm going to talk about steps away from deep learning is probabilistic programming, which is taking Bayesian inference, which is the gold standard approach for a lot of prediction problems, confidence intervals, and makes it easy. And so some of the things we talk about in machine learning just were not possible before, and now they are. And that's an amazing kind of innovation. But some of them were just really, really hard or really expensive. And now they've become so cheap that we can apply them to problems that were not only the most valuable problems in the world. And that is equally as innovative. And so this is a prediction made with Prophet, which is an open source tool from Facebook of atmospheric CO2. The values here are kind of scary, so I don't want you to dwell on that, but simply realizing that we can predict what tomorrow looks like because we know what today looks like, and it's probably very similar. But if we go out to 2029, our confidence in that prediction is much more variable because we don't know what the future really looks like, but we know how much we don't know, if that makes sense. And you can use this to think about portfolios of risky decisions, or again, real estate, which is always a depressing and fun thing to look at in New York. I don't know how it is here in Munich. But you can say, where can I buy a property for $1 million? And here's the distribution of likely properties. Again, a very depressing graph, but that's not the point. It's that you can get a distribution of outcomes with confidence intervals. And unlike deep learning, which is creating black box systems that do classification of things that perhaps were out of reach for us to classify before, this is an approach where you bring your prior beliefs, you take small, messy, heterogeneous data, and then you learn something about the world through machine learning. It's a really interesting paradigm of machine learning and something I think we're going to see more of in the next few years, which is why we're excited about it. If you're curious, our next project is on algorithmic interpretability, so how you see inside those black boxes. So now we're going to have algorithms running on black box algorithms to figure out how they work, which is, again, really cool and a lot of fun. I want to end with one thing that sort of blows my mind, which I saw this tweet. This is someone at the physical Amazon bookstore, right? So Amazon opened a physical bookstore. You can go there and buy books. All of the books are organized by data. So things that are highly rated on Goodreads, books with more than 10,000 reviews. This is data creeping out into the real world. So I think that's really cool. And so just thank you for bearing with me. I hope you enjoyed the technical piece, the people piece, the process, and the organizational stuff. And we have 10 minutes for questions if anyone has something they want to talk about. And so thank you. Someone going to be brave enough to ask the first question? We have this gentleman right here. I know there is someone with a microphone coming for you in a good way.
Google or YouTube is getting a lot of pressure because they place ads next to ISIS videos or child pornography, etc.
Yes.
Now you talk about image recognition. Is it so difficult, or are they just not trying?
It's very difficult because the machine doesn't know what it doesn't know. So you give it a set of labels to look for, but within the way this works is essentially that in deep learning you abstract out the human feature engineering process. And so you instead use a large amount of data and a large amount of computation to let the system learn for itself what about an image may indicate that it belongs in one category or another. And that means you don't control that process. And so there are a couple of examples of this going wrong. So one of them, in our interpretability work, we saw a great example in a paper about Lime, which is a system for doing this, that says, okay, we built a classifier to show, it tells you if something is a dog or a wolf. And it works really well, very high accuracy. But when they actually looked at what features were being used, it turned out that all of the wolves in the training set had snow on the ground. And so it wasn't classifying the animal at all, it was just the setting. And this is a good example of where the math is right, the output is accurate, and yet you're not getting a real result, and you wouldn't know that. And so you see issues like, I believe it was Google who got in trouble because they were applying the label jungle gym to Auschwitz, right? But it's algorithmically correct. It is very insensitive and very offensive. And so it's very difficult to say, you know, that this is a video of somebody working out and playing a game, and this is a video of ISIS. Like, that's actually very difficult to do in a purely automated way. Though I do hope, I know lots of people are working on it, and I expect we'll see significant progress there. And what I expect people will do is create automated systems to support the human beings who are doing the final determination. So to be able to flag things as potentially problematic, and then have a person review, and then take that data and feed it back into the next version of the system, and then perhaps that's how we'll get to the answer. Any other questions? Please.
Hello, I'm interested in this algorithm you showed before, that you have regressions and all that. And by machine learning, do you apply neural nets for training, or what kind of learning do you mean by that?
Which one was it?
Neural networks or nets? What do you use those kinds of models for predicting probabilities, or what kind of algorithm do you use?
So I believe firmly in using the right thing for the job, and that means earlier I talked about process. We write a very clear problem statement. You first start with the simplest possible approach. A lot of my work is in fact telling data scientists not to use neural networks because it's very expensive and the thing that comes out the end is uninterpretable. There are a few applications where it is the only viable approach, and that's where you choose to use it. And it's where a lot of the innovation in machine learning happens to be happening today. But it's by no means the only option or the best one for every problem. There are many, many other algorithms. Yeah. Can we get the follow-up?
Well, I'm a physician, and I read some studies about intensive care patients and predicting their mortality, and I've done a lot of work in this research in this kind of complexity world. And I think, as you said before, correlation is no causation.
Yes.
There are so many difficulties in just applying a regression
Yes.
to things. So I'm curious whether this approach with neural nets is already progressing so you can apply it, for example, in medicine.
So there are certainly applications in medicine, but where I've seen it being used most effectively are in domains where you could not apply a regression. So things like radiology diagnosis, in taking image or video data and applying a classification where the known set of classes is finite. So you only have a small set of labels you want to learn, and maybe it's cancer type A, cancer type B, not cancer. I'm not a doctor, you can tell me, but that's where you're seeing that particular technique applied. But as you say, one of the challenges is just getting the right data in a form where it can be used to actually make a prediction and then to interpret the meaning of the prediction. And so one of my colleagues shared a paper a few weeks ago around how there was a great example of this going wrong, where they were making a prediction as to which patients coming into the ER were at risk with pneumonia. And it turned out that the system ended up saying patients with asthma should be sent home. And the reason it said that was because when patients with asthma come into the ER with pneumonia, they get such good care that their outcomes are actually better than patients without asthma on average, at least in the United States. And so this is an example of where if you just follow what the algorithm learns from the data, you make a very bad decision. And of course, in healthcare, it's critical. In classifying pictures of cats and dogs, no one really cares. But you still need that kind of expert review and expert partnership to actually build these systems and have them work well. So we're not at the point where neural networks can take away any aspects of your job. Maybe they can help you a little bit, though. Great. Is that a question here, or no? I think we have time for one more. Okay.
Hi, thanks, Hillary. My question is more general. It's a general question. I come from academia. I wonder what's your view on the competition between industry and academia in terms of talent and data. I know many academia tend to leave university and join the startup. So what's your view on that?
So, I don't see it as a competition. I think it's two very different work environments and different cultures. And in fact, I think my company is a bit of a halfway house for wayward academics. So I work with many. But it really depends on what you're optimizing for. So in industry, you are working on problems that have generally commercial value. That is a constrained set of problems. In academia, you are working on problems that have publication value, a similarly constrained set of problems, but not the same problems. And so my friends who are working in academia are more able to work on problems around, like, how do we look at social media posts to predict suicide risk to actually help people? And there are, of course, commercial enterprises doing the same thing and nonprofits, but that's something, the problem domains are very different. The other aspect is that data is much more readily available in industry. But the data is constrained, whereas in academia, you perhaps can create data sets, you have just different opportunities. And so if you're thinking whether you should go one way or the other, I don't really see it as an or at this point especially. You can certainly move back and forth. And you can continue to do research while you're in an industry role and really try and find the best of both of those communities. Yeah, I don't see it as a competition. I do think it's unfortunate that it is so hard to pay people well in academia because we need people in those roles as well. Well, thank you, everybody. I'd love if you would all stay in touch. I'm Hillary at Fast Forward Labs or H. Mason on Twitter, and hopefully I will see you and enjoy the rest of the day. Thank you all for coming. Thank you.
Sticks and stones break my bones, but words
Thank
couldn't
you.
kill me. I'm